Imagine pulling a thin sheet of plastic from a small roll to wrap your lunch. It stretches effortlessly, clings to almost anything, and keeps food fresh for days. Most people never think about it again. But what if I told you this nearly invisible film begins its life thousands of meters beneath the Earth's surface, where ancient oil and natural gas have been trapped for millions of years? Think about this. Plastic wrap is only a few microns thick, yet protects billions of meals every single day across homes, hospitals, restaurants, laboratories, and factories. You can barely see it, but engineers spend years perfecting its strength, flexibility, and clarity. And this is where it gets truly extraordinary. Today, we're following the complete journey of plastic wrap, from underground hydrocarbons to one of the world's most widely used packaging materials. You'll step inside enormous petrochemical plants, watch molten plastic transformed into film thinner than human hair, and discover why producing something almost invisible requires astonishing engineering precision. What happens next surprised even experienced manufacturing engineers. Before a single roll reaches your kitchen drawer, scientists, chemical engineers, automation systems, and precision machinery work together around the clock. Every meter of film must meet strict standards for thickness, clarity, stretch, and food safety. Because if just one tiny defect appears, thousands of meters of production can be wasted. Most plastic wrap begins with crude oil or natural gas extracted from countries such as the United States, Saudi Arabia, Qatar, Canada, Norway, and the United Arab Emirates. These raw materials travel through pipelines, tankers, and rail networks to giant petrochemical complexes. There, engineers separate valuable hydrocarbons into dozens of different chemical building blocks. Most people never imagine that food wrap starts inside facilities larger than entire towns. Inside steam crackers, hydrocarbon molecules face temperatures approaching 850 degrees Celsius, or 1,562 degrees Fahrenheit. These intense conditions break larger molecules into smaller ones, producing ethylene, one of the most important ingredients in modern plastics. The glowing furnaces roar continuously, consuming tremendous amount of energy every hour. The purified ethylene gas then enters polymerization reactors, where millions upon millions of tiny molecules connect together into long chains called polyethylene. Imagine building an enormous train made from microscopic links. Those invisible chains give plastic wrap its flexibility, transparency, and remarkable strength. Without them, the film would tear apart almost instantly. Once polymerization finishes, the material cools into tiny plastic pellets measuring only a few millimeters across. Every single pellet contains carefully balanced additives that improve clarity, flexibility, food safety, and processing performance. A single factory may produce thousands of tons of these pellets every week before shipping them worldwide. But here's what nobody tells you. The pellets themselves travel incredible distances before reaching film manufacturers. Cargo ships transport them across oceans, freight trains move them inland, and trucks deliver them to production plants operating 24 hours a day. Something as ordinary as plastic wrap often crosses several countries before production even begins. Environmental responsibility has become one of the industry's biggest challenges. Manufacturers continue reducing energy consumption, increasing recycled content where regulations allow, and developing thinner films that use less raw material without sacrificing performance. Every micron removed from the film saves thousands of kilograms of plastic each year in large production facilities. Before entering production, every batch of pellets undergoes laboratory testing for purity, melt flow, moisture content, density, and contamination. Scientists inspect samples under microscopes and precision instruments capable of detecting defects invisible to the human eye. Because the next stage pushes these tiny pellets through one of the most fascinating manufacturing processes you'll ever see. Now the transformation begins. Millions of solid plastic pellets are about to become an ultra-thin, transparent film moving faster than a speeding car, all while maintaining nearly perfect thickness across hundreds of meters. And the machine that makes it happen looks unlike anything you've ever seen. The journey begins inside the extrusion line, where thousands of polyethylene pellets pour into a massive hopper every minute. Gravity feeds them into a rotating steel screw spinning at roughly 60 to 120 revolutions per minute inside a heated barrel. As the screw turns, it doesn't simply move the pellets forward. It compresses, mixes, and melts them into a perfectly uniform liquid plastic. The sound is a deep mechanical hum that never stops, day or night. Inside the barrel, temperatures gradually rise from around 170 degrees Celsius to nearly 230 degrees Celsius, or 338 degrees Fahrenheit to 446 degrees Fahrenheit, depending on the film formulation. Electric heaters and friction generated by the rotating screw work together to create a smooth, bubble-free polymer melt. Imagine thick honey flowing through polished steel pipes, but hundreds of times hotter. Every degree matters because overheating can damage the plastic, while lower temperatures prevent proper flow. Now comes the moment that defines the entire product. The molten plastic reaches a circular die where it emerges as a glowing tube only a few millimeters thick. Clean, filtered air rushes into the center, inflating the tube like a giant transparent balloon. Engineers call it a bubble, and maintaining its stability requires incredible precision. Think about this. That delicate bubble may stand more than 10 meters tall, while moving upward at speeds approaching 150 meters per minute. Air pressure inside the bubble often measures only a few millibars above atmospheric pressure, yet even tiny fluctuations can ruin the film. Laser sensors constantly measure its diameter, while automated controls make adjustments hundreds of times every second. As the bubble rises, powerful cooling air rings surround it from every direction. The plastic rapidly cools below its softening point, locking its molecular structure into place. You can actually hear the continuous roar of high-speed cooling fans echoing throughout the production hall. Without this carefully controlled cooling process, the film would collapse under its own weight. At the very top of the tower, guide rollers flatten the inflated tube into two perfectly smooth layers. Imagine squeezing a soap bubble without popping it. That's essentially what this machine accomplishes every second of the day. Precision rollers maintain constant tension because even a slight wrinkle could travel hundreds of meters before anyone notices. Next, the flattened film passes through automatic thickness scanners using infrared and beta ray measurement systems. These instruments inspect every centimeter of material, detecting variations smaller than 5 microns. That's thinner than a human red blood cell. What happens next surprised even experienced engineers when this technology first appeared in modern factories. If the system detects uneven thickness, automated controls instantly adjust the die opening or cooling airflow. The correction happens in seconds without stopping production. This closed-loop process allows manufacturers to maintain remarkable consistency over rolls stretching thousands of meters long. Most people never realize that computers continuously reshape the film while it's being made. The finished film now travels toward high-speed winding stations. Massive automatic winders carefully roll thousands of meters of transparent film onto cardboard cores while maintaining constant tension. A completed master roll may weigh several hundred kilograms, yet the film itself remains almost invisible. Watching it spin feels like watching glass wrapped around itself. After winding, automated converting machines slice the massive master rolls into familiar household sizes found in supermarkets. Circular blades moving with micron-level precision cut dozens of rolls simultaneously. Every cut must remain perfectly clean, because even tiny edge defects can cause tearing during use. Workers continuously inspect the finished rolls before packaging begins. By this stage, the plastic wrap looks complete, but appearance alone isn't enough. Engineers still need to prove that every roll meets strict standards for stretch, clarity, cling, strength, food safety, and durability. The next department uses artificial intelligence, laser inspection, and laboratory testing to find defects invisible to the naked eye. And that's where the real challenge begins. Now we enter one of the smartest rooms in the entire factory. Every roll of plastic wrap passes through AI-powered inspection systems equipped with high-speed cameras capable of capturing thousands of images every second. These systems search for holes, wrinkles, contamination, gels, bubbles, and microscopic thickness variations that human eyes could never detect. Most people never think about this, but even a defect smaller than a grain of dust can ruin an entire production run. Next comes laboratory testing. Engineers cut samples from every production batch and stretch them until they break using computerized tensile testing machines. They measure elongation, tear resistance, cling performance, puncture strength, and optical clarity. Every result must fall within strict international food packaging standards before the rolls receive approval. Thickness matters more than you might imagine. Household plastic wrap typically measures between 8 and 15 microns thick. That's nearly 10 times thinner than a sheet of ordinary paper. Factory sensors maintain tolerances within just 1 or 2 microns because even the smallest variation changes the film strength and stretching behavior. Not every roll survives inspection. Depending on the product grade, manufacturers reject between 1 and 3% production due to microscopic imperfections. Defective material rarely goes to waste. Instead, many factories recycle clean scrap directly back into the manufacturing process, reducing material loss while maintaining strict quality requirements. But here's something machines still struggle to do. Experienced operators can often hear subtle changes in the sound of the extrusion line before sensors report a problem. A slight change in vibration or motor pitch immediately tells them something inside the process has shifted. Decades of experience still outperform artificial intelligence in moments like these. Only after every inspection, laboratory analysis, and safety check does the factory package the finished rolls for shipment. Robots stack cartons onto pallets, automated vehicles transport them to warehouses, and logistics software schedules deliveries worldwide. Yet the incredible journey of this simple-looking product has only just reached your local store. Let's zoom out to the global picture. Every year, manufacturers produce millions of tons of polyethylene film used for food packaging, industrial wrapping, agriculture, healthcare, and logistics. The flexible packaging industry generates well over $250 billion annually, with demand continuing to grow across nearly every continent. A product you use for seconds belongs to one of the world's largest manufacturing industries. China leads global plastic production, followed by the United States, Germany, Japan, and South Korea. Together, these manufacturing powerhouses produce enormous quantities of polymer materials that supply industries around the world. Millions of engineers, operators, technicians, scientists, and logistics workers contribute to this massive supply chain every single day. Think about this. 50 years ago, producing consistent plastic film required constant manual adjustments and highly experienced operators. Today, artificial intelligence, laser scanners, digital sensors, and automated controls monitor nearly every second production. Factories now produce more film in one day than many older plants once made in an entire month. Did you know that if the plastic wrap manufactured globally in a single year were unrolled into one continuous strip, it would circle the Earth countless times? Did you know that some industrial plastic films are engineered to stretch several 100% before breaking? And perhaps the most surprising fact of all is that scientists continue developing recyclable and bio-based alternatives that could transform the future of flexible packaging. We've traveled from ancient underground hydrocarbons to one of the most sophisticated production lines in modern manufacturing. You've watched tiny plastic pellets become an ultra-thin film through heat, pressure, precision engineering, and constant quality control. The next time you pull a sheet from a roll, you'll know you're holding the result of chemistry, automation, and decades of engineering innovation. The next time you hold one of these in your hands, remember, it didn't just appear. It was born from the earth, shaped by fire, perfected by technology, and approved by the strictest standards in the world. That's not just a product. That's a masterpiece of human engineering. If you want to go deeper into the hidden world of manufacturing, tell us in the comments what product you'd like to explore next. Like this video, subscribe to the channel, and we'll see you inside the next factory.